I just wanted to welcome everybody who's online and who's at the Department of Earth and Planetary Sciences and the Institute of Meteoritics in Northrop Hall to the CASA Moon Planetary Sample Science Seminar Series. The seminar series is sponsored not only by CASA Moon, but also by Survey, the Institute of Meteoritics, and the UNM Grand Challenge program. And I'm delighted to be able to introduce the director of the Institute of Meteoritics, Dr. Carl Agee, who will be, his talk is Research Treasures in the UNM Meteorite Museum. Carl, it's all yours.
Thanks a lot. Um, and hello to everyone out there on the internet. Welcome to UNM. Yeah, as Chip said, I'm going to give an overview of some of the our meteorites in the UM Meteorite Museum, and also the connection to the research we do, and hopefully also the connection to CASA Moon. And just to get the presentation started off on the right foot, I have here a slide of a spectacular encrusted ferroin and northicite called Gadawa 001. And I'm going to be talking a little bit more about that later on in the talk, but that's the starting slide. Now, just wanted to say a few things about the University of New Mexico Meteorite Collection and also IOM. The collection and the museum reside within the Institute of Meteoritics here on campus at UNM. And the Institute of Meteoritics was founded in 1944 by Lincoln LaPaz. And at the time, it was the first institution in the world devoted exclusively to the study of meteorites. And of course, over the past 80 years, it's expanded its mission to become one of the leading centers for not only presenting meteorites to the public, but also research on planetary materials, and also studies and exploration of Mars, the Moon, and other solar system bodies. And this is a photograph of our museum, which is open to the public. So if you're on campus or ever visiting Albuquerque, you have an invitation to come by and take a look at this, what we think is a really, really fabulous display of meteorites for outreach and education. So I just wanted to, before I launch into some of the lunar meteorites that we have and other meteorites that are research interests, I just wanted to say another few things about the Institute. So the Institute, its original collection was put together by Lincoln LaPaz, and one of our probably our most notable sample that's on display and is part of the collection is the Norton County Albright. This is an Albright that fell in 1948, and it fell in Norton County, Kansas. It came in at 1,073 kilograms, and it's the largest achondrite meteorite in the world. And here we have pictures of what it looks like on display in our museum with children for scale. There's also a couple of very old photographs, black and white photographs, of Lincoln LaPaz and his crew bringing the meteorite to UNM, basically transported in that truck from Kansas back in the 1940s. So that was an amazing acquisition for the collection. And as I said, we have a number of what I would call historical meteorites, meteorites that come from that era. Here's another notable meteorite from New Mexico. This is called Pasamonte. It's a polymeteorite, and this is another fall. This fell in 1933 in New Mexico, and it's this is spectacular fusion crusted sample. It's just a unique specimen. And so anyway, when I arrived here back in 2002, there was this already well-established meteorite collection, and several hundred named meteorites made up that collection. But there were also, when I was looking at the collection after I'd been here for a while, I realized that there were also gaps in the collection with regard to especially achondrites, for example. Even though we had something like CASA, there were many notable chondrites, but we had very few meteorites from the moon and from Mars. In fact, only just a couple. And so after a few years, I discovered, really, taking upon the idea of doing meteorite classifications in order to acquire new meteorites for the museum and for our collection, and also, of course, for research. And so since about when I first started doing this in 2009, up until the present, I've classified 804 new meteorites. And these are all published in the Meteoritical Bulletin. And the other really advantageous part about this is that all of the meteorites that I classified end up as type specimens that reside in the UNM Meteorite Repository. They're there for research requests, for allocations, they're there for posterity, and they also greatly enhance the collection. So it's probably doubled in size because of this. And just to highlight that, so far I've classified 104 lunar meteorites and 54 Martian meteorites, but also a whole bunch of other types as well. And the payoff is just, having great enhancing the collection and so on, but it's also a great source of new research. And so when we get new unique meteorites that come in, that really expands our understanding of meteoritics. In this case here, I wanted to highlight the meteorite and Meteorite 7034, which is the first sort of polymic breccia from Mars. And again, all of that is due and came about basically from classifying that meteorite to start with, and then realizing it was worthy of further pursuit and research. But let's focus for a little bit on lunar meteorites, because that's at the heart of CASA Moon, of course, lunar samples in any case. And so I just wanted to show you a list of the lunar meteorite deposit samples at the Institute of Meteoritics that were acquired through classifications. It's actually 104 samples now. This is just a little bit outdated. So there are a couple of different categories that I've made into different colored columns here. And you can see that the greens are sort of the basaltic. There are only about 7 of those. They're quite rare. Then there are anorthosites. And these I would call the very pure anorthosites, not ones that are mixed up with a lot of other clasts and so forth. Then there are these troclolytic anorthosites that appear occasionally. And then in the blue columns, the 3 blue columns, you see the lion's share of the lunar meteorites are Highlands breccias. And these have been in the past classified by me, but also by others who came up with this term as feldspathic breccias. But in reality, what they really are mostly fragmental breccias, impact melt breccias, and also regolith breccias. Right, and so there are a bunch of those. If you want to look up something in our collection, you can go to our website. But the quickest and easiest way is to go into the Meteoritical Bulletin, and it's a somewhat searchable database where you can type in, for example, here's lunar meteorites from all countries, and then just to find the ones that Carl Agee had something to do with, you type in Agee into the text, and you get back all the lunars that I classified, and so you can just see which ones these are, and you can use that as a tool to decide if you want to request a sample from UNM. You can also use it to request samples from other repositories. Okay. So let's move on to look at some of our samples. I'm going to highlight ones here that I think have really a high likelihood of being research objects. through the classification process, they've been, they've been identified as lunar meteorites. Some basic microprobe data has been acquired, oftentimes oxygen isotopes, but typically there's a limit to what you can do in a classification, and so there's lots more research to do on very important samples. I think this one, Argon 002, is one of these. It's a lunar meteorite that is actually in the classification online. It says it's a norite, but I think actually it's a gabbro-norite. It's an equilibrated rock, and even though we've never seen there's never been a witnessed fall of a lunar meteorite on Earth ever anywhere. So this is one of the peculiar things. Even though there are more lunar meteorites than Martians, there still has not been a fall that has been witnessed. But when you look at this meteorite, you can see that it looks almost like a fresh fall. The photo on the left shows this very, very beautiful glassy fusion crust, and a broken surface shows this very fresh interior. It's crisscrossed with shock melt veins, and then that white region, of course, is the gabbro-norite. This is a really, I think, potentially a really interesting meteorite to study further, also because it contains, it has rare earth element rich meteorite present, and it also has zircons present. So this would be a meteorite that would be potentially good for doing in situ age dating, for example. And again, it falls, when you look at this plot of various, of some of these plutonic lunar rocks, Apollo primarily, of course, you can see that Argon 002 plots in the vicinity of the gabbro-norites and the norites on this plagioclase versus MG number and matrix minerals plot. Okay, let's move on to the next one. And that is this one is called the Gashar El Faroa 001. It's a lunar meteorite basalt. I called it a Mare basalt. I'm not sure if it's actually from the frontside Mare regions, but it really resembles those from Apollo. And it is particularly interesting because it is a intermediate titanium Mare basalt. Our preliminary data show that it has about 7.4 weight% TiO2 in the bulk composition. And this is the highest TiO2 bulk composition of any known lunar meteorite, as far as I know. And most lunar basalts in meteorite form are low titanium basalts. And as I showed you in that previous slide, there aren't that many. There are, people are saying nowadays, well, there are almost 700 classified lunar meteorites. They're getting to be so common, but actually there are some lunar meteorites that are still extremely rare, and those actually are the unbrecciated basalts. Those are very, very rare indeed, and remain so. Okay, next one I want to talk about, this is the Gato 001 sample that I showed in that opening slide. And this is an amazing ferroanorthosite. In my opinion, it's amazing for a couple of reasons, but one of them is that it is extremely pure in the sense that it is unbrecciated. That's not to say that it hasn't experienced shock. Of course, all meteorites that get lifted off of the moon are going to experience shock, and maybe they would experience shock even before that on the lunar surface. But this one is not heavily brecciated at all. And if you look at the top middle slide, you can see that the exposed surface shows this to be sort of a granular, sugary looking surface that is extremely uniform throughout. It, of course, is mostly made up of plagioclase, anaphytic plagioclase, but it has scattered throughout the olivines and pyroxenes, which you can see in the lower right-hand transmitted light photomicrograph, where you can see the higher relief ferromagnesium minerals. And then there's also a layer there of fusion crust that you can see in the lower part of that section view. Again, this is beautifully another just like the norite that I talked about a little bit ago. This one is very fresh. It's not a fall because yet again, was not witnessed. But when you see a meteorite like this with this incredibly fresh fusion crust, that means that it is has not been subjected to heavy desert weather. And what is so amazing about this one, I mean, this is just apart from science, it's just amazing to look at. It's got this, the fusion crust is green, you know, and it's, you know, typically when we think about meteorite fusion crust, you think of dark glassy fusion crust, but because of the high amount of hydroclase, with just a sprinkling of ferromagnesium minerals in there, the fusion crust ends up looking like this instead of black. And again, I want to emphasize why this sample is, I think, so special is because even when we look at the Apollo collection, the ferrite anorthosites typically are very heavily brecciated. This is 60025, and you can see, and there's thin sections next to it on the right, and the specimen at JSC on the left, and you can see that this is heavily brecciated sample, so it is not as uniform, for example, as Ottawa is in that regard. Here's another example of a so-called ferrite anorthosite, and actually it's the class 3A that was focused on in this particular study. So you see there's a lot of other stuff that's mixed in with it. And again, oftentimes what we have to deal with are heavily brecciated rocks from the lunar surface. And when you get something that's not brecciated, then that's something quite special. Even the lunar, other ferrite anorthosite, lunar meteorites, are always heavily brecciated. For example, like NWA 429 and NWA 12695, which are part of the UNM meteorite collection. And so then the question is, where is Ottawa 001 from? And how could it tell us more about the history of the moon? Of course, we know where the Apollo 16 sample came from that I just showed you. We don't know where Ottawa came from. Maybe it came from the far side. Maybe it's another sample from the near side. It would be really interesting to see what kind of age date we would get off of this to see if it corresponds well with the Apollo 16 samples, or maybe it shows us something different altogether. Sadly, we don't know where it's from on the moon, but again, it's part of the piece of the puzzle until we get full samples of the whole lunar surface. I just wanted to show you this picture because this is actually a picture of what most lunar meteorites look like. I mean, this is a beautiful meteorite. Don't mistake it. It's gorgeous. But again, this is a heavily brecciated sample. It's got tons of shock melt in it. It's got various clasts. It's a typical fragmental breccia from the lunar highlands. And then I want to finish the lunar meteorite segment of this talk with focusing on, or just telling you a little bit more about another lunar meteorite that I classified a while back. And this one's classified as a regolith breccia. And it has, when you look at, so the first of all, when I got this sample, it arrived from North Africa in a big box, actually in a cooler that had been duct tape shut, and then an address to me in Casitas, New Mexico. And I opened it up and there was this 10-kilogram rock sitting in there. So they sent me the whole thing. And at first I thought, what is this? This is just a boulder, you know? And, but you know, if you look at that upper right-hand corner photo, you see there are these little scallops, and actually those I'm pretty sure are the leftovers of regmaglyphs. And there's no fusion crust on this one. But then finally, when it was cut into, I ended up getting some big slices from the person who owns it. And those big slices show this incredible breccia on the interior, and what jumps out at you is all this orange, you know, and it turns out that that orange is highly altered. It's looks to me like it's altered olivine, and it gets. We haven't done any, you know, we would check to see how much water is in it or anything like that. But when you do microprobe analysis on those phases in there, they come up with low totals like 87, and then you know, a fair amount of aluminate in there, and so on. So it looks like some sort of altered olivine. And I don't think that this is actually, I mean, you know, I can't prove it right at this moment, but I don't think that these altered grains are from desert weathering. I really don't think that. So this would be a really interesting sample to check for, to see if there's maybe some sort of lunar water in there. No one's done DAH on any of these samples, on this particular sample. So I think this would be a really, really interesting one to delve into more deeply, and try to connect it up with the possibility that there are such things as altered, aqueously altered lunar rocks. I know, for example, the rusty rock that Chip has told me about on many occasions. That's another one of these. So again, maybe this is a similar sort of story. Okay. I'm going to leave lunar meteorites behind, and because I wanted to spend the rest of the talk highlighting other types of achondrites that are in our collection, and they are not, you know, this is just a sampling. There are many, many different stories that I could tell about unique samples that we've acquired over the years. But this is a group that is sort of forming over time because we're getting more and more samples of these so-called silica-rich achondrites. And, you know, it started off actually back, you know, maybe, what is it now? A while back, in the case around 2006, when GRA 06128 was recovered from Antarctica. And that was, I think, one of the first tracheandesite achondrites to ever be found or to be identified as such. And but then in the meantime, we had Alma-Hattasita. Maybe that happened around the same time, but Alma-Hattasita had many different lithologies in it. And there was one lithology in there that was, you know, it's a small sample. And the picture of it in the lower left-hand corner is this tracheandesite that is in the Alma-Hattasita fault. Interestingly, I've received, you know, recently, not too long ago, a really nice specimen, which is shown in the upper left-hand corner, Northwest Africa 15820. And it turns out that sample is very, very similar to the Alma-Hattasita tracheandesite, very, very similar indeed, major elements, rare earth patterns, etc. And again, it's one of these ungrouped achondrites. I also classified Northwest Africa 11119, which is a alkali depleted andesite. Erga-Tuila 001, which is an alpatite. That sample that's up there in the third from left is actually sort of pinkish orange. And if you would see that lying in your backyard, you would just think it's some sort of, you know, granitic rock or something. And it was sent to me, and that's what I thought it was at first. I just thought it was some random earth rock that a nomad had picked up and thought it was a meteorite for some reason. I mean, you would never think that it was a meteorite, but anyway, they pick up everything, I guess. And so it was sent to me, and I was still very skeptical about it, even after doing some pro work, but I sent it over to Karen Ziegler in the stable isotope lab here at UNM, and she ran oxygen isotopes on it. Lo and behold, there's oxygen isotopes that are very far removed from the terrestrial fractionation line. It's absolutely, without a doubt, a meteorite, right? And so, so again, doing classifications, of course, you need to have a microprobe to do these. But having an oxygen isotope lab is like so empowering because you often find yourself in a situation where you're just scratching your head and you can't decide one way or what this is. And then the oxygen isotopes are such a great way of helping you narrow down what the possibilities are for these unknown samples, these new samples. And the same was true for Northwest Africa 11575. That's another tracheandesite, but it ended up plotting not where those other ones plot on the oxygen isotope diagram, but it plots up with the ordinary chondrites. So this is probably as an ordinary chondrite precursor, whereas the others come from other parts of the solar system. And then there's also Erdchef 002, which is an andesite and ungrouped. And this one came on the scene not too long ago, declaring it, the authors who published that research on Erdchef declared it as being the oldest achondrite in the solar system. And actually that title was held by Northwest Africa 11119 for a while, thanks to collaboration with Mini Wanwa's lab at ASU. We had an age on that was also very ancient. And so anyway, there's a little bit of competition there on who has the oldest achondrite in the solar system. I'm sure there is another one out there somewhere that's even older. But in any case, these silica-rich ungrouped achondrites all have in common the fact that their bulk composition plots somewhere between 55 and let's say 65 weight percent SiO2. So they're not basalts, they're not a typical achondrite that is either mafic or ultramafic, but these are evolved rocks. And but you can see also in this diagram, this is the volcanic rock diagram of total alkali versus silica. You can see that the total alkali contents of these is highly variable, with the highest being in ergotuila 001, of course, because it's made up mostly of aldite. It's got a very high sodium to potassium ratio. And then, but then you have NWA 11119, which has very low sodium plus potassium. These, even though they're all evolved achondrites, they're just looking at this diagram, you might guess that they are not from the same parent body. And but that's also been confirmed. That's been confirmed through oxygen isotopes. Yet again, here we use oxygen isotopes to further differentiate these collection of silica-rich achondrites. And it's clear from the way that these plot on the del 17 versus del 18 oxygen isotope diagram that these look like they represent a collection of different paraploids. It's kind of interesting. I mentioned NWA 11575. Yes, that plots way up high on the diagram above the TFL, up where the ordinary chondrites plot. I think more like the L's or LLs. And then you have this collection of samples that all sit on that cap delta 17 equals -1 line. There's a concentration of them near delta 18, 8 or 9 in there, where we have again the Alma-Hattasita sample. We have NWA 515-820, which is like it, but then you also have that very depleted 11119 sample. They all cluster right around the same spot. I don't know if that means whether they're from the same parent body or if it's just fortuitous. But ergotuila, even though doesn't have the same delta 18, it does have that same cap 17, about -1, but it sits further down on the diagram. And then you have for Czech and GRA, they plot in just below the TFL, sort of in the realm of just above, say, for example, HEDs and braconites and so on. So what do we take away from this? Well, there are a number of things that you can think about when you see this. First of all, you come to the realization, based on the ages of these, that these samples are telling us that the early solar system had bodies that were forming crust mantles and cores very early. And not only were they just a one-shot deal where you get a partial melt of a primitive meteorite composition, let's say, for example, and you form a basaltic crust, let's say, or an ultramafic crust. These actually have, again, these evolved crusts. So they look like they have gone through maybe multiple episodes of melting and remelting, distilling out more silica-rich magmas on those parent bodies. This is 11119 that I'm whirling around on with my fingers under, and you can see how interesting this sample is. Just, you know, you never think this is a meteorite. You just picked it up off the ground. But in any case, it was age dated at around 4.565 billion years. And so this is, you know, roughly 20 million years older than the Earth. These things were forming before the Earth formed. And so this comes into the whole story, or contributes to the story of how planets end up getting formed the way they form, how accretion operates. You know, the classic idea is you get these small undifferentiated bodies, they all come together in a large body like a protoplanet, and then it goes through some sort of internal melting or magma ocean where it turns itself inside out, and you have a crust mantle in the core. The fact that you have these smaller bodies already forming crusts and cores before the planets are forming may argue, for example, that some of the planets, maybe even Earth, was formed not by small undifferentiated bodies, but by differentiated bodies that already had cores. And so they went in to form the Earth as a heterogeneous collection of objects, not all of them necessarily the same composition. Okay, that's all I wanted to say about those silica-rich achondrites. And now I want to move into the last segment of the talk and present tell you about some Martian meteorites that we've brought into the collection through classification. And this is Northwest Africa 12522. It's a Martian basaltic sugarite. You can see from the photograph, again, this is, you know, not all meteorites that come from the Sahara are weathered to bits, you know. This is another one of these unbelievably fresh finds. And it is covered with beautiful glossy fusion crust, meaning that it is probably, you know, hasn't been on Earth very long. And also, this is a really nice hefty sample. You know, it filled my whole hand. It's a big, big piece of Mars. And then the other part of this is that this particular meteorite had multiple stones that were collected. And so there's a stream field out there in the Sahara where these things are. And sometimes when we get deposit samples from collectors and from meteorite hunters and so forth, we get a slice, or we get, you know, a bag full of crumbs, you know, things that are all ground up. And then once in a while, we get a deposit sample that is a beauty like this one. This is a deposit sample that is a 25-gram complete individual. So this is a little beauty that was sitting out in the Sahara. And it's got, you know, basically 100% fusion crust, with the exception of maybe a couple of pieces that flaked off. But in any case, the beauty of the sample. Okay, so why is this sample interesting? Beyond the fact that it's a gorgeous Martian meteorite, it's actually very similar to QUE 94201, which is one of the classic Antarctic Martian meteorites, in that it's a highly evolved basalt. And that highly evolved basalt characteristic is very well demonstrated using a pyroxene quadrilateral and plotting up the probe data for the pyroxenes that are present in the meteorite. And that's of course been done with QE 94201. It has this very striking it has these striking trends where you have cores that are magnesium rich, calcium poor, and then they trend up to calcium rich, diopsidic, and then the ribs are like ferropygonite. And lo and behold, 12522 has the identical trend in it. And so that's shown on the left-hand diagram there with the red circles. Those are all probe data. And it looks practically the same as QE 94201. So, for example, I don't know how easy it is anymore to get QUE 94. And I was looking up its total known weight. And there's 12 grams of it, right? That was, I think, the original mass was 12 grams. So this is like super, super rare. And to request a piece of that study is, asking a lot of the curator. NWA 12522, on the other hand, like I said, is a collection of stones. And altogether, those stones, what I call pairs, that the whole mass of that is around 9 kilograms. So there are 9,000 grams of this. Some of it held in private collections, some of it in deposit samples like at UNM. But in any case, there's a lot of material that's available for the scientific community to do all sorts of studies on if they so wish. So that's another one of the powers of having these Northwest African meteorites is that they're finding really, really large samples and then lots of times multiple stones. Okay. Let's move on to another Martian, but what I'm going to show you next are two Martians that are not typical Martians. And this is the other thing that my mind became open to when I first started working on NWA 7034, the polymeric breccia, is that the Shergottites, the SNC meteorites, the Shergottites, the Knocklites, and the Chaffingites, a marvelous collection of meteorites, but probably quite limited in regard to representing the diversity of igneous rock types on the planet Mars. Okay, so my view is there's way more to Mars than SNCs. So NWA 7034 demonstrated that, it's AKA Black Beauty. And then, and there have been a couple of others like that. I think there's more to come. But this is something that was just so odd, but it belongs to the Martian story. And so I'm going to explain to you what this is about. I gave a talk at LPSC on this meteorite. And this is just a couple of slides out of that talk. So this is what you're seeing in this picture is a 465-gram meteorite that has two distinct lithologies. It's got what I call a light lithology. And I've taken the liberty of circling in yellow on this diagram that light lithology. It's this sort of greenish patch in there with the dark fusion crust on it, and maybe a couple of other patches here and there. And then there's a dark lithology, which is actually the host rock, the host meteorite. The light lithology makes up probably about 15% of the total surface area. We've also done CT scanning and looked to see how deep this is. And we think that, from the preliminary scanning, that it penetrates a significant way into the interior. And then there are probably also a few isolated clasts of this also scattered into the host. So what are these made of? Well, these are made up of two meteorite types that are totally different. So that light lithology, so of course I focused on that light lithology because it was so striking, so that's sort of human nature. You look at a rock and you grab the part that looks the most interesting, and it may not be representative. But anyway, that's the first piece that I chipped off of there. And I gave a piece to Karen Ziegler, and she came back a couple of weeks later with the results. Where did that plot? It plotted in the SNC array. So the light lithology here on this plot of del 17 to del 18 shows the yellow dots. Those are the analyses that turned in on the light lithology. And then I gave her a piece of the host, which I call the dark lithology. And that, because I was excited, I thought, oh, you know, first gave her the light lithology. And I thought, oh, this is Martian, wow. And so that dark thing is also going to be Martian. Awesome, you know, because typically when you get a polymeric breccia, the polymeric breccia is made up, I mean, there are a few exceptions, but mostly polymeric breccias all have the same oxygen isotopes because it's from the same parent body. And all you're seeing in there are different lithologies from the same parent body, so they'll be different petrologically, but they don't have different oxygen isotopes. So I was expecting this whole thing to be a Martian meteorite. And it came back as plotting with the LL chondrites, the dark lithology. So the light lithology and the dark lithology are coming from two different parent bodies. And that's my interpretation. And so what does this mean? Well, it's, I think it's very exciting. First of all, let me just talk a little bit about the light lithology. The dark lithology is basically, I don't have time to go into gory details about that. The dark lithology is basically a highly equilibrated LL chondrite. I couldn't find any chondrules in it, but it's got a typical highly equilibrated LL mineralogy. The light lithology is Martian, based not only on the oxygen isotopes, but also on the microprobe data that we did. And this is a backscatter image of that. And the light grains in there are olivines. The dark gray are mascalinite. There are a small amount of augite in there, a small amount of chromite, small amount of apatite. This is a Martian troctolite. Okay. At first I thought it was a Martian dunite, like a chasugnite, but it's actually a little different. And I'll explain to you what I mean by that. So this is a triangle that's used to classify, you know, plagioclase, rich, plutonic rocks, you know, basic to ultra basic. And it shows, of course, plagioclase at the top apex, pyroxene to the left, olivine to the bottom right. And the chassignites, there are three of them that exist, three known chassignites. They'll plot, of course, down where olivine, near the olivine apex. Turns out actually that one of the chassignites is not actually a true dunite. It's a peridotite, but let's not worry about that for a minute. The Madani HEM 002 is a little less olivine rich. It has more of the mascalinite in it. And so that plots in the troctolite field there, number 8. Let me just talk a little bit more about the three known chassignites. So it turns out that the original chassignite chassigny itself is oh, let me go back. Come on, go back. Yeah, is a dunite. So is NWA 2737. That's the black chassignite, and then the 8694. That's a wurlite. And so anyway, whether or not HEM is a chassignite or not, it's not really, I don't think it matters a lot. What really matters is that it's Martian, and it is, at least as far as I can tell, the first Martian troctolite. Okay, so we went ahead and decided to run with this, try to understand how this could possibly be. And well, somehow a Martian rock got mixed up with an LL rock. One possibility is that an L chondrite asteroid impacted Mars, and the escape ejecta mixed these two things together, formed a meteorite that formed an object that ultimately crossed Earth orbit and was recovered as a polymeric meteorite. We can take this even further and hypothesize that this sample is actually sampling a giant impact orbital debris cloud, a mixture of Mars and LL. And maybe, again, this is a hypothesis, to be tested, that it is somehow related to the moons Phobos and Deimos. Originally, Phobos and Deimos, some of the early ideas about it were that they were captured asteroids. More recently, people have been thinking that perhaps that's not the case, that in fact, they're the remnants of an impact. And if so, you would see some Martian crust mixed in with something like an ordinary chondrite or a chondrite type composition. And that's a testable hypothesis, of course, because there's going to be a Martian moon mission that's going to be carried out by the Japanese, and they were going to be able to test these two hypotheses. And part of the story may be this meteorite. We'll have to wait and see. And now I'd like to finally wrap it up with the last sort of unusual new type of Martian meteorite, and this one is a vesicular basalt called NWA 16272. And you can see that this meteorite is full of vesicles, some of them quite large. The vesicles themselves are, you can see within them, you can see the sort of spinifex quench texture. When I got this from Northwest Africa, it was sent to me by a meteorite hunter, collector, dealer, who said, "Oh, this is a new angrite," because angrites have vesicles in them, and he thought this was an angrite. He said, because we found it in a place where we had previously found an angrite that had classified for it. When I got this, and first thing we did is, of course, probe it and send it over to Karen for oxygen. It's not an angrite, not at all. So what was it? Well, it was, the probe data showed us that it was highly likely to be from Mars. Iron manganese ratio is a dead ringer for Martian rocks, Martian basalts. The results that Karen sent to me, I came back with, really blew me away, because I was thinking, okay, so it's going to plot with those red dots where the SNC sit. But where did the oxygen data plot from this vesicular basalt? They plotted right on top of NWA 7034, which is of course, that's the polymeric breccia that I talked about earlier. It's not only that it plots close to it or near it, it actually forms a mini array within the turquoise array that the Black Beauty NWA 7034 forms. So it's just like right on top of it. And so this led me to the conclusion that this is also Martian. It's just not from the same oxygen isotope reservoir as the SNCs. And then this is where it plots on the total alkalis versus silica diagram. It doesn't plot where Black Beauty plots, which is that green. That's the bulk for Black Beauty, which is that turquoise with the error bars by the GRS and the Spirit rover data. It plots sort of in the higher alkali end of the SNC meteorite. And this one is still under study. We have still many things that we're trying to figure out about this one, but it's an example of a new type of meteorite from Mars that, we found because of the, all the fabulous meteorites that are coming back from Northwest Africa. Okay. And now I just want to finish with this final slide. Hopefully we have a little time for Q&A if there are any. The one thing I told you about being able to allocate samples for the community, for research scientists, wherever they are worldwide. We have a lot of Black Beauty. We have a lot of NWA 7034. And this is thanks to a meteorite collector who has very generously has donated individual uncut, unclassified specimens of Black Beauty. And here's one that we received just a while back. It was a 252 gram full uncut, undisturbed stone of NWA 7034. It's of course pairing because there's only one NWA 74. That's the original 320 gram, I think it's 20 gram single stone that I classified originally. But there are a whole bunch of, there are several of these stones that were collected in the strewn field in the southwest, the Western Sahara. Anyways, I just wanted to mention this because, again, part of our collection is not just to be outreach to the community, to have a meteorite museum. It's also for research, but not just research for Carl Agee. it's research for everybody who wants to participate. And so we're really open to collaborations, but also, you know, if you want a sample that we have and we can possibly supply it, we will do so gladly. And I think I'll stop there and take questions.
This is a long one. Do you want to read it? Carl, are you planning to XCT scan NWA 16272? Since the vesicles are so spherical, it would be interesting to try to calculate gas species loss based on vesicle abundance and size like McCoy et al. Did for other basaltic meteorites.
Yeah, we have actually, we found a partner in doing meteorite scanning at Goddard. And so we've had this one, we had that particular basalt scan there, and but you're right, this is a really important tool to have in order to get a handle on what's on the interior of them, but also to do quantitative studies like the ones that you mentioned.
Any other questions? Feel free to just shout them out.
Speak out.
Yeah.
I'll say something, ask a question. So, Carl, spectacular. And, you know, with the perseverance collecting samples, unfortunately, Chris Hurd is kind of in charge of summarizing what we've collected so far with perseverance. So he's writing a paper right now to summarize the collection up to now. We're just getting ready to head into the greater rim, which should be very exciting to get crustal rocks sampled. And Zach and I are going to be keeping an eye a little bit on that. But the data keeps coming in, and the new meteorites keep coming in. So comparing the samples to the meteorite collection is going to be very important to do.
Yeah.
And I think that having access to a number and doing this comparative research, and the combinations could be very important. Unfortunately, I mean, the people who would do the rover stuff, really, most of them, virtually, very few of them have any idea about meteorites. So,
Right.
So it's going to be up to the community that's represented here today to do a lot of that comparison work and to try to also think about the implications of these different samples. You know, we've talked about it for years, some of the different chemistries on the surface of Mars.
Right. Yeah.
So, do you have any comments about what some of the newer implications you think for the history of?
Well, I touched on it before. I think it's been recognized for quite some time now that SNCs are not necessarily representative of the average Martian crust, and given the fact that, Mars is the surface of Mars is the same amount of surface as all the continents of the Earth, right? So I kind of doubt that SNCs tell the whole story. And we're seeing that again with a few of these very rare meteorites. I think, again, that couple, obviously, some of these crustal rocks we never get as meteorites just because they're too fragile. The only way you can get those is with the rover. I think the fact that we have somebody like Chris Hurd who's involved in this is fantastic. Chris is a UNM alum. He's worked on Martian meteorites, so I feel happy with the fact that he's intimately involved in all of this. So,
hey, Carl,
yeah.
You had a couple A chondrites and had really low capital 17 values. Is there anything else like those?
Which ones do you mean?
You showed a plot with all of your
Yeah.
triple isotopes, and there were some of the A chondrites were like -2 or -1, or I don't remember. They were
-1.
And what else is down there?
Urilites, but also a bunch of things like there are Acapulcoites, Lodronites. Those are more like primitive achondrites.
Yeah, okay.
But they might, you could make the story that they're from some very highly varied large parent body that no longer exists. I mean, if they're all on the same Cap Delta 17 line, one could make that argument, just like you make the argument for TFL, or you make the argument for the SMC array. So, I think the jury's still out on this, and we keep finding more and more, and a lot of them do plot on that -1 line. And so I think that's very intriguing. Yeah, yes.
And there was a question from Michael Lucas. When you showed the meteoritical bulletin database screenshot, there was a column score. Can you please explain?
I think that the score is just simply it comes back with hits. So when you type in Agee text or something, it searches for everything it can find in the bulletin, and then it scores all of the finds. So that one page I showed you was just the tail end of the 2 other pages that were there. And they all get a score and how good of a match they were for the search. That's all it is. Yeah.
Relevance score?
Yeah, I think it's more like a relevant score. Yeah.
Any other questions?
One other comment, Carl. So since these are all shot, most of the meteorites we get are shot from the moon and Mars. The IOM does have an impact type collection. And I'm hoping sometime we'll be able to look at that again and improve that. I have a lot of the samples that could be accessed into
Sure.
collection, but of course that gets back to resources and support on the curation side. And how do you view the situation and what is the prospects for continuing or getting support from NASA and such for this kind of work that you're doing?
Yeah, I mean, I may be wrong about this, but I don't think it's a high priority for NASA, supporting hunting for new meteorites. You can go to send a mission to Mars and hunt for new rocks on Mars. But, aside from the Antarctic program, which is supported by NASA and NSF and so forth, I don't think that there's a real focus at NASA on the treasure trove that's coming out of the hot deserts. I mean, it's truly mind-boggling what's come out of North Africa. As far as diversity, completely blows Antarctica out of the water. Even though I love the Antarctic collection, what we've seen coming out of the Sahara is just, in terms of new types of meteorites, it's unparalleled. So, yeah, that's my answer.
Regarding the large group of lunar breccias you showed, are there any pairs in there?
Oh, yeah. Yeah, they're pairs for sure.
And can you do anything about getting rid of breccias separated from the other ones? It's not the same thing.
It's unfortunately, breccias, as you know, are hard, it's like going down the rabbit hole lots of times when you start looking at them, because there are many, many different class and lithologies in there. And so when you do a classification of these regolith or fragmental breccias, it's just a very superficial inventory of what's there and what you think it is. And each individual regolith breccia could be a whole master's degree or something, I mean, some of them are so complex. So a lot of what you see in the Met Bowl is just the very top slice of information. And it doesn't go into depth at all. And so even deciding which ones are paired is a challenge. But for sure, there are going to be pairings in there. Absolutely. There are now, I think, somewhere between 600 and 700 lunar meteorites that have been classified. And I'm sure that a lot of those, you can shrink them down to the pairings that there might only be, a couple hundred at most.
And there's a big difference between spathic fragmental breccias and regolith breccias, or at least you be able to separate those.
Yeah. But again, the trouble is you get a small sample of these. When I study it, I get a deposit sample that, I can hold in my hand. It's probably coming out of a gigantic boulder, And so is that representative of the boulder?
Request from
Who knows? I might actually be getting some of these highly biased. So it's sometimes tough. Breccias can be very tough to work on in terms of actually getting a definitive answer. So anyway, I think that's probably good, right?
Yeah, doesn't
Okay.
look like we have any other.
Yeah, it was a lot of fun.
Thank you,
everybody.
everybody. Join us
See you-
again next
See you
week.
later.
too.
Bye.